Good. I started the recording, so we can start. So first, this is the last but one lecture given by me. I think you still have some hours to be taught by Professor Archetti, I think. And you may agree with Professor Archetti on the dates of the exam. I think that there is no problem to make the exam in May as soon as possible, and as soon as you like, I mean. In principle, you may know that we cannot, we cannot record an exam before the end of the lectures, but after the end of the lectures by Professor Archetti, can make it. And you are first students only, so there is a lot of flexibility. And but especially for Erasmus students, I think it is useful if you have opportunities to take the exam as soon as possible. Also, next week, I am teaching my last lecture on Wednesday, and I will also open an evaluation by students of my teaching. It can be compiled online, so it's not necessary that you come here to fill the form. The only thing I really rely on your filling the form, because you are few students only, so it is extremely important. And I think what I will do is to open the evaluation next Wednesday, and then left it open for a couple of days up to Easter. So it is recommended next week that you close it, you make it, okay? And it is particularly important for me because evaluation is useful to me to understand if I did a good job. And it's just personal. I really like to get the feedback from the students. And then I'll explain to you in a formal way how it is used to allocate resources by the universities to the departments and how the data are used, basically. But just to make a summary, usually the front page, it's numbers. It's statistically analyzed and then used by the university to allocate resources to the department. The real page is text, and this is just run by the professor. The university, unless there are some particular situation, doesn't read them. They are not statistically analyzed. So basically, if you want to send a message to the university, numbers, front page. If you want to send a message to the individual professor, it's the real page. So, but I will explain better next Wednesday. But in case you are not here, just keep in mind that you can listen the recorder. I will explain how to fill the form at the beginning. You can listen the recording of the lecture. I will record it, and then you will just kindly ask you to fill the form as soon as possible. Okay. Good. So you need a code to fill the form, and we'll give the code to you next Wednesday. Good. If you don't have any question, I think we can start with the teaching. Very good. So last week we started with the design of drawings, and I explained why they are extremely important for both harbor engineering, design of harbors, and beach recovery and protection. So I rushed at the end of the lecture. You remember that after the narrative description of what is the purpose, drawings, and what results, what change we expect in a beach profile after the construction of drawings, then we started talking about the procedure, the design procedure, which is the most interesting part for us because we are engineers and therefore we need to focus on the design. But, and you may remember that I talked about 12 steps. I had to rush, so I want to start again and to spend a little bit of more time, especially on the technical steps. So Let me take the PowerPoint again. Today, we will not make any exercise any practical exercise. We will do one next week, okay? So after, as I said, a narrative discussion, these are the parameters that we need to size: length of the drawing, the spacing between them, elevation, porosity, tapering. Tapering means, in a way, the degree with which we reduce the width of the spine and coastline here. And this is our drawing. Tapering means that the width of the drawing is decreasing. So this is one parameter that we need to size. There are many reasons for doing that, and in particular, the user is a simple top. The user can control maybe looking there, therefore, construction must be designed in order to sustain a given load. And the angle to the shoreline, which would say is 90 degrees. This is the angle, okay. Because something is making like inclined, so you see here the angle. And the shape, whether we want a T-shape drawing, etc. So we talked about 12 steps. We talked about the lambda rule. This is our basis. Just I will recall this figure just to remind you. If here you have a high water shoreline, low water shoreline, design shoreline. Blue is the design shoreline. This is the pre-project coastline, and we associate the coastline to the berm. There is a slight difference, but of course we want to advance with the beach, and the degree we indicate with S the distance between the new low water shoreline and the pre-project coastline. And then W, the distance between low water shoreline and high water shoreline. We indicate with G the gap, with capital H, the width of the groin at the end of the groin, and with Z, the width of the groin along the body of the groin. Okay, of course, if the groin is not T-shaped, capital H is equal to Z. Okay, and then let's see these steps. So the first steps are very easy to describe, to discuss. Estimation of wave statistics, okay? And wave statistics, you know what is, the wave angle and the wave height and the characteristic wavelength and etc. And then step 2, identification of the extension of the intervention, extension along the coastline. And we discussed that these interventions should be kept as short as possible, because the longer it is and the higher the impact. Of course, we want a positive impact, but there are also negative environmental impacts and negative impacts on the visual of the coastline. So just try to reduce the length of the intervention, of course, as much as possible, of course, without compromising the success probability of the intervention. And this is the second step. And then step 3, identification of the design location of the post-project burn. This means that we want to estimate S. You may remember that we indicated with S distance between the pre-project coastline and the low water shoreline and so on. Just and make the figure. So we take some time to memorize them. This is the pre-project coastline. When we talk about pre-project coastline, we don't make a difference between low water and high water. Why? Because we suppose that if we need to make an intervention, if we need to do something, it means that the ocean is already in very pronounced way concerning a concerning ocean, usually means the beach is treated up to the what we consider a fixed point. Fixed means that, for instance, here we may have a seawall, or we may have a berg that is restoring. So we don't make a difference between low water and high water, because if the profile of the coastline is fixed, then it means that the high water will protect the ocean, the sea, and the low water levels will adapt. This is assumed to be fixed. Of course, if you have a different situation, doesn't make a big difference. You just need to take a reference coastline with respect to which you want to estimate your advance. Okay? And then we identify the low water shoreline here and the high water shoreline here. And this is the low water shoreline and the high water shoreline. And I think we indicated with W as distance and with S as distance. Now let me make a check, since I don't want to make mistakes. You see here, yeah, I was right, okay? So I'm just trying to repeat this figure so it's easier for us to understand. Okay, so now step 3. Basically, it is identification of the post-project burn means, according to our figure, that we want to estimate how long we need to advance. Because of course, this is the necessity to estimate that it's supposed to put a rectilinear drawing here. Okay. Let's suppose we're going to put a drawing here. Rectilinear is not this shape. And then what I have to do is to determine the length of the drawing by shifting seaward the top of the drawing change the gap. Okay. So first of all, we identify how much we want to advance, how long we want to advance. Step 4. What is the post-project slope of the beach? This is something that is not easy to be understood, because if you are in a section without the beach, it's difficult to estimate what the slope of the beach will be. Why it is important? So, because it dictates the distance between the high water shoreline and the low water shoreline. So, how can we estimate this slope? The easiest way is to look around for a place, a neighboring place, where you still see a beach, where we can still see a beach. And the suggestion is that we look at the existing beach. Take into account that after the intervention, after horizontal space, we expect that the beach is more gently sloped. This is quite obvious. If you think of a short beach, a very short one, is maybe quite sloping. If you extend this beach, then you will expect that it becomes more gentle slope. Okay. And now, step 5 is just subsequent, is prediction of the horizontal distance W between mean and watershed. Of course, this depends on the altitude shift that you are expecting from low water and high water, and the slope of the beach. Therefore, once that you know the slope, once that you know the wave statistics, sea statistics, tide statistics in this case, and estimate the distance W. We will see that it's why this is important. Because it's with the low watershed. You see that that doesn't special with respect. But you may need to check what happens with high water, because you don't want, for instance, with high water, that some maybe structures, infrastructures are reached by water. Therefore, explanation of W is important because I must that you know design the length of the ground. You can estimate with the number the position of the watershed line. Then the W can estimate to what extent leverage seawater is expected to get tight to get close infrastructures, structures, to things that you may want to keep dry. Okay. So far it's quite easy. Now, this is the start of the more technical steps. Step 6, identification of the number of beach cells, and the average as a consequence, gapped with G. So, why the number of cells has determines the gap, the average gap. This is clear because once that you determine the total extension, which we indicate with capital L, the capital L that you see there is the total shortfall length of the intervention. You determine the number of cells you want to split the length of the intervention, and therefore, depending on the size of the groins, you estimate the gap. So let's start on the easy equation. The total length, you see there, is equal to the number of cells multiplied by gap plus capital H. Okay. Let's suppose that this is capital H. Okay. This is a rectilinear drawing, so capital H is equivalent to what we indicated C. Then, if you have the gap here, gap G, I don't draw the next. I don't draw the next drawing. If you have the gap, then of course you take gap plus capital H multiplied by the number of cells that we got. This is very easy, okay? But if you have any question, because you know the easiest things usually are the more difficult to be understood, because you know you listen to the professor saying this is very easy, so people get depressed sometimes because they think, yeah, it's very easy, but I cannot understand. So if you have any doubt, please stop me. Now we can go to the next step. This is the page. Design of the top width of the groin. So here you have a repetition of the figure. Now, the design of the length and width of the groin, it is to be done with the lambda rule. Okay. Clearly, a T-shaped groin allows us to reduce the groin width because with a T-shaped groin, you shift the low water shoreline forward. Look at the figure because you see the difference between the groin without the T and the groin with the T. Measure vantage from the extreme end of the T, and therefore you get the low water shoreline closer to the head of the groin, at least in the vicinity of the groin. Then between groins, you may have a retreat of the profile, but this is fine, I mean, because it is also nice that the profile is a bit moved, okay, back and forth. And you can clearly see here that if you increase capital H, you get the low water shoreline closer to the extreme end of the groin. In some of the cases, we design, I anticipate, we design the size of capital H, so the size of the T, by imposing that the beach profile reaches the end of the groin. So what we could do here is, for instance, clearly, if you put a T here, if you put a T here, okay, and the T is very expanded, so let's suppose that the end of the T is here, and I want that lambda G, I place the end of the T to a distance lambda G. What I obtain in terms is that the profiles. See, this is my target. Okay. So in some of the cases, I know the goals. Now, how to estimate the length of the groin? By using the lambda rule, you decide. You want a T, not. If you don't want a T, you just estimate the position of low water shoreline, previous steps, and you put the groin forward at the distance of lambda G. Of course, you still don't know G. So let's move forward with the computation that is reported here. So let's start by designing parameter. Okay. So let's start with this. And you can determine this by thinking at the use that you want to put the ground. I will give you some orders of magnitude of the minimum that you can design. So you fix this, like in any design process, sometimes when you have many degrees of freedom, you start by fixing, by making some decisions based on technical considerations. So your decision will be, I want the width, the lowest possible value, and then I know what is the minimum that you usually got. To fix this, and then you can impose determine, lambda, okay, you can impose that Z plus lambda G times second value, and I think this is here, okay, Z plus lambda G, this is 2 lambda G, because here we assume that H is different with respect to C. So basically, if it is a T groin, the expression is like this. Okay, this is lambda G. If I want to impose that the beach profile gets the meter. This is lambda G. Lambda G, this is C. And this is again lambda G. So lambda G plus lambda G plus C is equal to H. And so after determining Z, if you want to make a T groin, you estimate H in this way. Okay. Now, depending on the decisions that you have made, you have all the size, the grounding. Depending on the decisions that you made, you can now determine G. And let me see where is okay. But let me go a little bit back on the web page because I want here in the PowerPoint I skipped a step of the computation and then it's not very clear. Let me just go back here and let me highlight what is the step that was skipped. Okay, and this is the step that was skipped. Okay, so the total length of the intervention is equal to n, which number of cells that multiplies the sum of the gap plus capital H. So basically, you get capital H plus the gap, and you get the next grounding. You multiply by the number of cells, you get the total extension. So this is an equation that allows you to make the first step. Still, we have two unknowns, capital H and G. So you cannot compute G. Our purpose is computing G, okay? And capital H is still unknown. So the stage you approach, even fix that capital H is equal to C, which means no T, and you fix T. Okay, so first option in this equation that I highlighted, okay, you put H equal to C, no T, and C is estimated by following some rules of thumb that I will give to you soon. Or the second option. Second option is what was highlighted here. You assume H is equal to 2 lambda C, which means that you want T. C is known, it's fixed, thumb, lambda is known. G is an unknown, but at this stage, if I go back to this equation, now I include, I plug it in an estimate for H, which depends on G. So I have on G that is unknown. I can estimate G, which is the gap. Once you have the gap, you can estimate the grounding length because it is rectilinear from the low water line. Otherwise, if it is a T-shaped, or you apply, in any case, the lambda root here, and starting from, and then the T of the ground is placed at the low water line. Is this clear? So the concept is you first design the length of the intervention, then you design the number of cells, and then you design the position of the new low water line. And then you decide, do you want a T-shaped groin or you want a rectilinear groin? If it is a rectilinear groin, it's easier. You just fix the width Z, and then you apply the equation that you see there to compute the gap. If it is a T-shaped, you just have to use the other equation in order to plug in each value there, depending on G. And then you estimate the gap again, and then from the gap you estimate lambda G, lambda gap, which allows you to estimate the length of the ground. Of course, you end up with a combination of and this combination is number of length of the interconnection, number of cells, and you end up basically on this subjective distributions. Just the number of cells, and put it there in the subjective gradient, yes. You end up with values for the output, and values for the length of the ground. And then you look at the whole picture, the horizontal picture. And you may say, no, the gap is too small, I want. So if you want a longer gap, you have to decrease the number of cells. Decrease, or case, and decrease the number of cells. Conversely, if the gap is too large, as we will see some numbers of length. In general, we say that less than 20 meters. So if you end up with a gap of 2 meters, let's try to reduce them. Another thing that we say is that we shouldn't keep a long distance between the grounds. Why? Because if you keep a long distance, there is no continuity in intervention. If you put one along, then another gap. Even if the grounds are very long, understand that if they are very far, it's unlikely that you get an advance of the beach for an extension of 1 kilometer. So if you say that the knee is 20 meters, usually we say that max shouldn't be more than 100 meters. 100 meters is very long enough to become visual. And you know, create the gardens and clean. So let's say that the interval of 20 to 100 meters is something that may be fine, okay? And then you also look at the width of the ground. If you see that the ground becomes too long, you know, becomes very long, with a width of 2 meters, which is about the minimum of what we say. Okay? For the top of the ground, we say that the top width shouldn't be less than 2 meters. But if it becomes a ground that is very long, you understand the stability may be compromised if it is too thin. Because you know, you can have a strong kind. It's a long distance, better to make a stronger structure. So we should look at the overall picture and compare the overall picture, the features of the overall picture, with what you can see in other interventions, with the rules of thumb, which we provided to you now, in order to see that the overall whole is coherent, is fine, is something reasonable from an engineering point of view. And of course, you have also to consider the visual bit. Now, here you see that there is, in this step, an additional computation. The additional computation is just the attempt to develop the resulting formulation for the gap, starting from, you see here, the number of cells, the overall length, and the lambda value. And it's just an attempt to derive an explicit computation for G. And in order to do that, you have to, of course, substitute in the relationships that we obtained before the resulting values for capital H, for some variables that you can eliminate, okay, from the computation. But here it is also assumed that you want, in a way, to take a safety factor, okay? And the safety factor is such that you are not just happy with the position of the low voltage line. You want to make a check with respect to the position of the high voltage. And therefore, what we introduce here is the value of W. So if you want that the high water shoreline reaches the head of the groin, the formula becomes this one. So 2 lambda G plus W, which means that you shift the beach forward of the quantity W. Okay. In general, so if we do that, then the formula for computing G becomes what you see on the screen, where I visualize a new variable, capital X instead of W, where 0, the capital X is in the range 0 W. So what is capital X? It's a safety factor. Okay? So if you want really to that the high water shoreline reaches the end of the groin, you put X equal to W. Otherwise, if you are happy with the low water shoreline, X is equal to 0. Okay. Now, if you make a substitution, then you get that the total length of the intervention, capital L, is equal to, sorry, W is here, and I adopt. So what is X? X is something in between. Yeah, in between. Okay. So basically, if I want to bring the high water shoreline to the end of the groin, you understand that the measure of the groin should be advanced seaward, because I have to advance the whole new reach. So basically, let me just try to make other field here. Okay. A project. Let me see if the blackboard is in the camera. Just 1 second. Let me do this. Okay. Now the blackboard is in the camera. Perfect. So this is pre-project. Where the low water shoreline. And then here the high water shoreline. Okay. And then the groin. And this is the lambda G that I used so far. Okay. But what happens here? It happens that with the high water shoreline, with the high water, the water is not here, but becomes placed here, okay, for the high level of the water. So what is the overall story? The overall story is that if I want that with the high water shoreline, I get to this level, I have to advance the low water shoreline. So basically, the low water shoreline has to go here. And of a quantity, if this is W. If I want to reach the high water shoreline this level. If I want to show line to advance W. I also to advance the low water show line of W. Of the same quantity. And therefore, the ground has to go further. Has to go further, same quantity W. Is this clear? Because if I bring a going forward, I bring forward the water show line, and then I bring forward the water show line. Okay. Of course, another possibility is that instead of bringing the growth, I decide to adopt the this is what is assumed there. Okay, because you see that capital H is recomputed in this way. In the former case, it was capital H equal to G plus Z. Now it's 2G plus W plus Z. Because I want here, instead of advancing W, I want to advance instead of I want to make the T as large as the previous value plus W. And then if you, at this stage, if you allow that W is variable, because I don't necessarily want to advance with the high water show line the full W, but I wanted to advance quantity X, then I substitute. Instead of W, I use the X value where X is between 0 and W. Okay. 0 if I don't want to advance it. So I am happy with this solution. But if I want to bring the water show line X forward, then I can say that the total length is estimated by using that equation. So N, it's multiplied the gap plus 2 lambda G plus 2x, because X is the elongation. This becomes my X elongation of the T on one side, on the side. So L times N times G plus 2 lambda G plus 2x plus Z. And this is the total length of the intervention. And here our purpose is to find an explicit computation for G. So you make these computation steps, and then you get this formula. If you put X equal to 0, you go back to the previous solution. So you don't have any advance. And depending on what? Z, L, number of cells, you compute the gap. And then with the value of the gap, the growing rate. Okay, now you see here that, but let me go back to the PowerPoint. Here is the computation. Now, here it is discussed the consideration that I did. I mean, if the gap width is too low, too small, then we may decrease the number of cells, okay? Or we can think of other solutions, like if we adopted a value of x that is too large, we can decrease it. And just keep in mind that, as it's written here, less value than 20 meters for the gap are not generally recommended. Okay. One thing for recreational beaches, H should be much lower than G, because otherwise it means that if you cover half of the gap with the head of the T, it's not nice, because then you get half of the gap is covered by the left groin, half of the gap is covered by the right groin, then, I mean, the space left free between the T's is too small. So this is why we say, okay, if you want to adopt a T-shaped groin, it is a fine solution, because it means that the groin is less extended seaward. On the other hand, it means also that the free sea, the free space between groins is decreased, and we don't have to decrease it too much. Okay. Now we have to position the heads. So heads means the end of the groin seaward. And then we have to study the orientation of the gaps. And we said that the line crossing the gap should be aligned with the dominant direction of the wave crest. Okay, this is much better. If we get the waves entering straight between the groins. And then step 10, we have to make an estimation of the impact of extreme waves. Where do we get water when extreme waves come? Because even when we talk of the high watership line, this is an average high watership line, which is usually computed based on the tide. And now we have to account for the fact that when we get wave storms, of course, with the wave run up, we get the water reaching a position that is beyond landward, beyond the high watership line. Therefore, we have to make sure that if we have some exposed structures, infrastructures, people, we have to make an estimate of the impact of extreme waves. And sometimes you have also to make an estimate in terms of erosion. What happens to this, to the beach? Does it get very eroded during the extreme events? And this is to be done through a computation, which we don't discuss, of the across-shore sediment transport. So we have formulas for computing the sediment transport along shore and the cross shore. And by using these formulas, you check what happens during extreme event. And then we move to the estimation of the position of the landward head of the groin that is extended to reach the berm. And then we make sure that the end of the groin is buried into the berm. Okay. Just to make sure that we don't have a bypass by currents during extreme events of the head of the groin, landward, beachward, which would be really not good, because it would trigger a local erosion there. And then step 12, the elevation of the heads, which should be determined to minimize wave overtopping during the extreme event. Or otherwise, if we decide to allow for wave overtopping, of course, we have to estimate what is the impact of wave overtopping. We can tolerate it. If it is very infrequent, we can tolerate it. But in any case, we have to determine the elevation of the groin by studying, analyzing the impact of overtopping. Here you see an indication. In the case of a rock structure, rock means boulders, the crest elevation should be not less than 1/2 arm of stone diameter above the predicted design profile plus some contingency. interpretation of this sentence. You predict the design profile of the beach, and then if you make the groin with boulders with 1 meter of diameter, you make sure that the top of the groin is at least 50 centimeters above the design profile of the beach, with some safety factor, some contingency. So 50 centimeters, let's bring it to 75 centimeters. It is the classical safety factor of 1.5, which is fine, okay? This is an indication in the case of a rock structure. Good, so these 12 steps are, in principle, are very simple. The only complication is this computation here, but it's not a conceptual computation. It's just that you need to take a paper and make this computation by plugging in for each unknown variable the related equation for the computation, and then you develop it. But it's really very simple. Okay? It is made complicated by the fact that there is lambda, the lambda rule, and there is also safety factor X here, but otherwise it's very simple really. Questions? I think if you don't have any question, we can see how the drawing is done. And we can see typical values for the variables that you see here. So the top width, which is indicated here with the left capital B. And then we have the elevation of the groin above the mean sea level. Here it's indicated with respect to the mean sea level. The elevation of the groin with respect to the beach profile, because you see here lowercase h is the height of the groin from the foundation, beach profile, to the mean sea level. And then with RC, we indicate the elevation gap between mean sea level and the top of the groin. The groin usually has a foundation. The foundation is something that is harder than sand, because if you put the groin over the sand, then of course the boulders of the structures tends to get deeper into the sand, because the sand is not really strong. Okay, so what we want to do is that the foundation is stable, doesn't get deeper, and therefore usually we put a foundation that is made by material that is a bit harder. It can be concrete, or it can be with boulders, with a material that is harder than the sand. And usually we put also a layer of geotextile over the foundation, which is a kind of stabilizer for the distributing the pressure. Because you understand, if you made, usually these are made by boulders, so the pressure of the self-weight of the groin over the foundation is not uniformly distributed. And for this reason, we put a geotextile in order to homogenize the pressure of the groin over the foundation. Usually we have an inner part of the groin called the core that is less permeable, in order to make sure that we reduce the permeability if we want to reduce it, because we know that it's also a possibility to make the groin permeable. But usually what we do is to make this inner part less permeable and also more compact in order to reduce permeability. So typically, if we decide to go with natural boulders to make the groin, the inner part, the core, is made by boulders of smaller and smaller size. In order to reduce the permeability, we reduce the gap between the components, the individual components. On the other hand, given that these components have lower diameter, they are more exposed to erosion. And for this reason, we don't want to use this material in the layer that is directly exposed to waves, and therefore we put big boulders around in order to protect it. Okay, in terms of suggested dimensions, orders of magnitude, here you see the same figure that is replicated with a lower size. So these are the rules of thumb, orders of magnitude for the size of the groin. Let's start from B. And here you see width of the groin top from 3 to 6 meters. Earlier I said 2 meters. It's also possible 2 meters, but I mean, you understand the order of magnitude is this one. In some of the cases, we want to be able to walk over the groin, for instance, also for touristic reasons, and therefore, of course, we have to protect it to avoid the people fall into the water and to make it a bit larger. So this is the order of magnitude of the top width. When we talk about H, the depth of the basement with respect to the mean sea level, it's from 2.5 to 4 meters. Of course, in the part of the beach that is more landward, you may have a much lower value. We refer to these values from 2.5 to 4 at the seaward end of the groin. Okay, so you understand that at the end of the groin, the difference, the height of the groin with respect to the foundation is between 2.5 4 meters. This is the highest elevation 4 meter that we foresee for a groin. Okay. Now, RC, which is the height of the groin top with respect to the mean sea level, from 2.5 to 1.5 meters. Okay. Of course, when you get close to the beach, you have the bottom of the sea that is gaining elevation. Usually the groin is at the same elevation, and you get a much reduced elevation of the top of the groin with respect to the sand. But usually we keep anyway an elevation of the top with respect to the sand, which is more or less equal to RC. RC, so from 0.5 to 1.5 meters. And this is more or less equivalent to half of the size of the boulders that we use. Usually, these boulders have a diameter that starts from 1 meter. We use large blocks, okay, because we want them to be very stable. Now, the depth of the groin basement landward, okay, with respect to the mean sea level is indeed, this reflects what I just said, is from 1 to 2 meters, which means that, of course, landward you have a reduced depth. The slope of the groin size is from 1.1 to 1.2. Okay, 1.1 means 45 degrees. Usually it's considered to be too much. Okay. And not only for reasons of stability, we will study the stability of the armor units later, okay? But it's not only a problem of stability, it's just also the fact that, you know, if you have people climbing up there, 45 degrees is a slope that if a person falls down, it's impossible to stop, okay? They start rolling over and over until they reach the sand. And this is something, you know, you have to be careful because if it is a very small elevation of the sand, that's fine. But if it is a couple of meters, you may want to avoid people fall for 2 meters because it may be dangerous. And so usually, I mean, 1.2 means something like, if I well remember, it means that for 1 meter of elevation, you gain 2 meters in the horizontal direction. I think it is like 33 degrees, something like this, 30 degrees. So it is, I mean, it is more reassuring. The thickness of the foundation is from 0.5 to 1 meter. So this is the typical scheme. Okay, now let me just go back to the web page because I want to make sure that I'm not forgetting anything. Okay, now there is an interesting discussion that we may make to close this first chapter on groin design. what is the additional and I mean interesting discussion that we may make? If we want to model beach evolution with a more refined approach with respect to the landing, what should we do? This is interesting because indeed the landing is a rule of thumb. But when you make a design project, very often you are required to make a numerical modeling of the beach evolution after the intervention. Indeed, this is what also guidelines. So, rule of thumbs are usually fine for preliminary design, for getting a first idea. But then, you understand, the Lambda rule cannot be applicable everywhere. We cannot expect a high precision meet. So people may ask you, local authorities may ask you to check the evolution of the beach profile with a more refined approach. And these more refined approaches usually are make use of numerical models. I mean, they make use of mathematical models, and I say numerical models because the solution of these mathematical models usually it's not an analytical solution. It's not possible to solve them with an analytical solution. We need to solve them with a numerical model. Or otherwise, and this is something that is usually a solution that is usually adopted, you may check the evolution of the beach with a small scale laboratory, which means that you replicate your intervention, the coastline, the beach profile, in the lab in a small scale. Small scale means that you reduce the geometric scale in order to be able to represent into the lab a longer portion of coastline. Usually we use scales ranging from 110, which means that a coastline of 1 kilometer becomes 100 meters long, and it's still too much for a lab. Usually the pools in the lab have a size that is ranging from 20 to something 50 meters. If we adopt, usually the upper range of the reduction in scale is 1/100, which means that a coastline that is 1 kilometer long becomes in the lab 10 meters long. And then with a wave generator, you generate waves into this pool, you put sand there, and you simulate what is the effect on the beach of the grounds. This is an approach that was largely practiced in the past to study the final configuration of beach recovery strategies. Why largely applied in the past? First, because the costs were less relevant. But the main reason was that numerical modeling in the past was not possible because we had available computers for the last 30 years only. And if we go much further into the past, it was not possible to make a numerical computation. There is to say that depending on the conditions, the uncertainty of small-scale modeling in the lab is lower with respect to the uncertainty of numerical computation. This is why laboratory models are still much used, even if the cost is really relevant. Let me see if I can check over the web, and let me see, because I think there are some links here. I don't think so. So let me check if I can find a video. There is a laboratory in Delft Hydraulics, who is in Europe is the largest center that does these experiments. And it is quite old, 1927. Let me see if I can find some videos, probably not here. Videos, okay. maybe this one. Let's see. This is not the Delft one, but still the video, I think.
Used today, validating and optimizing the design of a small company's green infrastructure, such as the whole time and where conditions are best related to technical performance of the new design and what an unintended impact such structure may have on developing areas. The impact of future climate change and sea level rise can also be tested in these physical models. The facility was established in the late 1960s and since then, the CSIR has successfully completed countless physical modeling studies. The complexity of the investigations range from determining the safety and accessibility of tidal pools to verifying the designs of complex breakwater structures for the ancient ports of South Africa. Many international studies have been carried out on lines of 40 meters to 30 meters by 50 meters, accounting for the largest area in the facility. A divided wall between the two faces can be removed to create one large 3,000 square meter area to make it one of the largest unobstructed hydrogen test areas in the world. The size of these wave basins allow wind reports and elements to be tested without risk of significant failure events. The CSIR basin is by total state-of-the-art instrumentation, including FR and single mile wave vehicles that can be set up to create a 24.
You see the beach up there?
To integrate energy in the basin. These wave vehicles can generate demand multi-direction from state to stimulate naturally occurring storm events. The wave vehicles are capable of generating significant wave heights of up to 0.25 meters and water depths of up to 0.8 meters. The range and versatility of these facilities allow high-power and multiple wavelengths available for a variety of purposes. High-power also has wide ranges commonly used for conducting the complicated.
You see the beach? That is.
The CSIR wave solutions can be adapted to accommodate body particular models. These include ones that are superless, others, waves, large. This is adequate to a wide range of research and consulting projects.
This is the lab in Delft, Danish Hydraulic Institute. Just 1 second to wait for the advertisement. This is the wave generator. This is the study of an energy converter in order to get energy from the waves. Here they are testing a coastal defense, you see. A wave energy converter. This is again a wave energy converter. And this is a drawing. Here they are testing the stability of the Harbour units. You see that they have a shape that is geometrically complex in order to favor the joints, the joining the various elements. Okay, that's it. So as I said, this is a possibility. So you test what's going on. These tests were mainly related to testing the stability of the structure, not to test the evolution of the beach. But there was one of the tests in the first video that indeed were simulating also the sediment transport. Simulating the sediment transport is complicated because, as you can understand, one thing is to generate waves of clean water against a structure, and another thing is to also put some sand into the water. What is the main problem with these models in terms of operationally? The main problem is the fact that you cannot reduce the scale too much, because if you reduce the scale too much, the movement of water becomes viscous, not more turbulent. And if you turn to turbulent movement, turbulence, to viscous movement, it means that you are not reproducing the reality, because in the reality we have turbulence. And of course, turbulence, as you can understand also, based on your intuition, turbulence slows down when you reduce the scale a lot. Like if you want to create turbulence in a glass of water, it's not easy because you don't have enough space. And viscosity in the small spaces prevails. So this is the main operational problem. Now let's go to the numerical models, and you will quickly understand what is the limitation. And let me refer to this scheme here. This is what is called one-line model. It is a scheme of the most used model in numerical models for studying the beach evolution. And what is here the driving concept? The driving concept is that when you get a longer short sediment transport, and you see here the red arrows, the black arrows, you have some Q, which means the flow of sediments incoming, and some flow of sediments outgoing, Q out. So if Q in is larger than Q out, there is a positive balance of sediments. And this positive balance means that a certain volume of sediments is accumulated in this infinitesimal length of coastline. And you see the accumulated volume here in yellow. Okay, so this is quite straightforward. You have more sand incoming than sand outgoing. You have an accumulation of volume, and you have to start this accumulation at the very local level in a very small length of coastline. So you see a delta there, delta y. Delta y is the length, infinitesimal length of the coastline. Why we need to work at the very local level? Because this model provides an average impact and an estimate of the average accumulation of sediments in the considered volume. So if you make the difference Q in minus Q out in a longer portion of coastline, you understand that you lose the details, the fine details of what happens here. If you just measure sediment in and sediment out from here to there, then you get an average estimate of the volume that is accumulated along the table, but you don't know if most of the volume is here instead of here. So if you want to work at the very local level, you have to, numerical modeling, you have to approximate the equation on very small pieces of domain. And therefore, this is very small, but this is fine because, I mean, with the modern computational resources, you can really apply this piece of modeling many times. But the big question is how I estimate the geometry of the accumulated, because I can estimate the volume, the value of the volume, like I have 1 cubic meters of sand that stays there, but how to estimate the geometry of the volume, of the accumulated volume. And the one-line model makes a very simple assumption. The assumption is that the beach profile in the vertical direction remains unchanged. So if you see this parallelogram here, you see that the slope of the beach, of the pre-slope of the beach, is the same as the post-slope of the beach. And to be more detailed, the beach profile in this line here is unchanged before and after the accumulation of sediments. So if you make this assumption, then you define the general geometry, this volume. And if you know the yellow volume, you can now estimate the advance of the beach profile, the accretion, delta C here. And this estimation is possible because we assume that the beach moves forward by keeping the same profile, same slope, same curvature, and it just moves forward by keeping the same geometry. And then we can estimate this delta C at each time step, because of course the flux of sediment varies from time to time. So we have also to work on small times, okay, like 3 minutes. Every 3 minutes, we compute the advance, and then we move forward, as I said. And at any time, we need to use wave statistics that allow me to compute this Q in and Q out. The formula for computing the sediment transport based on wave statistics, we don't discuss. And we don't discuss these formulas. But I just want to say that this kind of model allows a very simple equation, something that we can apply into R. If we knew wave statistics and sediment transport statistics, it's very simple. And we know the profile of the beach. We keep the same slope, and then it's very easy. This is an example of the one-line model. It is very known. It is the first example, the first model that was developed for studying beach evolution. Now there is another model available, which is called the Genesis here. And it is about 40 years old. It's a bit more complicated than the one-line model. We don't go into the details. I just want to say that there are commercial models that allow you to make these computations. There is a strong approximation there. Okay? I mean, in some of the cases, especially if you believe that there is strong heterogeneity of the processes, it's much better to go in the lab. Okay. Okay. One final thing, permeability. And this is how permeability is computed into Genesis. Let me see the PowerPoint. I don't think, let me see if I have the formulas here. Let's forget this. Okay, permeability. So what do we need to estimate actually in order to apply these models? We not only need to estimate sediment transport. If we want to put a groin into a model, we cannot assume that the groin stops everything, all the sediment transport. This is not realistic. Also because, you know, if you assume that the first groin stops everything, cannot work, because actually it is the sediment transport is mitigated by a sequence of groins. It's not just stopped. So we have to estimate the quantity of sediment that bypasses the groin. Bypass means that seaward, there is some sediment that they get against the groin and then they turn around. Okay. This is called bypass, or the bypass may be from overtopping. Okay. And then there is some sediment that may go through the groin. When the groin is made by movements of concrete, we assume that the permeability is 0, and this means that also the flow of sediment through the groin is 0. But if the groin is windows, is permeable, then we have also to estimate permeability. So we define we estimate permeability and bypassing with the two coefficients, P for permeability and B for bypassing. And these two coefficients are in the range 0, 1. 0, P equals 0 means no permeability. P equal 1 means that all the sediments go through the groin. Bypass 0 means no bypass. Bypass 1 means that all the sediment bypass the groin. It's clear that they are mutually exclusive because if you have permeability 1, you have no bypass because all the sediments go through the groin and therefore there is no bypass. The same applies for B1. If you have a full bypass, there is no permeability. So the fraction of sediment that goes on the other side of the groin is simply estimated with this formula. So P, which multiplies 1 minus B plus B. Okay. So what doesn't bypass, then in percentage of P goes through permeability. And the bypass just goes to the other side. Now the question is, how we estimate P and B? First of all, you see that this relationship satisfies the constraints that I just mentioned. Let's assume that P is 0, then the fraction of sediment that goes on the other side is given by B, where B is between 0 and 1. Perfect. The same is if B is 0, you see that the fraction F is given by P. P is again between 0 and 1. Now the question is how do we estimate these two? And P values are suggested by the literature for typical groin shapes. And groins made by boulders have a P value that is close to 0. Okay. And here there is the estimate of P. Depending on DG and DLT, what is DG? DG is the sea depth of the groin seaward end. DLT is the depth of active longshore sediment transport, which can be assumed to be about 1.6 times the significant breaking wave height. Therefore, when you know the wave statistics and you know the DG sea depth at the groin end, then you can estimate B. Okay? You see that the larger the sea depth at the end and the less the bypass. Because keep in mind that if the sea is very deep, the sediment transport typically collapses on the sea bottom in the vicinity where the sea is less deep. When you have a strong depth, then it means that you have less bypass. And the opposite for the DLT, the depth of active longshore sediment transport. Okay, and here there is actually, you see here a very simple formula. Once that you have F estimated and you have the sediment transport longshore estimated, QG, you compute the fraction that goes on the other side of the groin. So to summarize, P permeability given by the literature and bypass estimated with this formula here. Good. Now, other models have, of course, different formulations, and therefore this is just an interpretation, very simple one that is given, that is used by this model. Okay, let me check if there is something more that can be said about this. Okay, and let me see. Okay, we can forget this. This is a formula for computing the max depth at which you have sediment transport in the sea. You see that there is a max depth. If I go beyond that depth, there is no more sediment transport. And the very simple formula adopted by the Genesis model is max depth of sediment transport is twice H max. H max is the maximum annual wave height. Okay. Okay, I think that's it. And before we make the break, let me anticipate just briefly what is the next step is to study the stability of the rock and concrete armor units over the grounds. Okay. And this is the subject of, I would say, not sure, maybe next hour, next couple of hours. But now let's make the break and let's meet again in 15 minutes. Any question? Yeah. You couldn't see the slides? Let me see, because maybe that I forgot it. Let me just check. Should be here, design of drawings. Let me just check. Okay, open the web page. Yeah, I think it is here. So they didn't. Yeah. Okay, the PowerPoint slides, you find them in the bottom of the web page here. Download the PowerPoint. Okay, perfect. Okay, thank you. Yeah, I know that they are not directly available on virtual. I know that. Okay, and then, okay. Perfect. I need to go back to this. Okay, anyway, we meet again at 3. Good. I stop the webcam and microphone. Okay, I think we can restart. Let me just clean the backboard. Okay. So we're talking here of stability of rock and concrete armor units. Let me just check. I think I have a PowerPoint here as well. No, there is no PowerPoint here. Okay, good. That's fine. And rock and concrete armor units. First of all, we make this discussion, assessment with respect to groins and breakwaters. So one key question about these structures is their stability against strong weights. Stability by taking into account, of course, how they are built up. And we make explicit reference to what is largely the most frequent structure for these protections, which is the assemblage that is obtained by putting together armor units, boulders, and boulders or other units that are made by armored materials. So here you see an image of tripods. So these are artificial units that are used in order to build barriers. And you can find many other examples if we look for, just 1 second, if we look for armor breakwater, and we look for images. Okay, here you see that they can be made by natural harbors, like this one that you see on the right. Okay, you see here. This is an armor breakwater, and this is natural armors, or they can be made by artificial units. And you have an example here. These are units that are called, I don't remember the name, but I will give you soon the name for these. I think they are tetrapods. And here you see that the structure is a mix between tetrapods and, oops, sorry, tetrapods and natural boulders. Okay, so we have tetrapods seasides and natural boulders on the land side. This is a solution that has been adopted, in my opinion, based on my understanding, in order to offer higher resistance to waves and a more good-looking visual on the land side. And here you see that there are many other possibilities with in this case, let's see, these are artificial units as well. This is a picture that is very small, so I'm not expanding. But for instance, here you see another solution with I'm not sure whether they are tripod or tetrapods, artificial structures. What is the reason for using these artificial structures? First of all, to maximize the linkage between the individual units, because with this complex geometry, it's easier that they link each other. And another reasons for using artificial units may be the need of saving natural boulders, especially in regions where you need to transport them from a long distance. It's quite expensive to travel long distances with these natural boulders, and in this case, it may be cheaper to make these artificial structures. So now we are talking of the stabilities of these. You see, there are many possible solutions. Here there is another nice picture. And you see that we may have a lot of fantasy in order to devise the geometry of these units in order to maximize their reciprocal linkage. Now we are talking of the stability. Of course, the stability is a key feature, and when you build these structures, it's essential that you make a check of robustness, of stability against the strongest waves. And this is what we study today. Okay, there are several approaches that can be followed in order to analyze the stability of these units, and this is a branch of structure. A branch of technical application that is located in the larger domain of sediment transport. Sediment transport, sediment stability. Of course, these are not sediments. These are units that are aware in a similar situation as sediments that are moved by water. Sediments that are moved by water may be stable, meaning that the water flow cannot mobilize them, or unstable, meaning that they can be moved and originate sediment transport. In this case, it is a similar problem. We have to check that these units, like sediments, that are exposed to violent flow are stable or not. Of course, if they are moved, they don't originate sediment transport. Their quantity is limited, but still, if they are moved, it's a problem, and like in the case of sediment transport. And in any case, as I said, the analysis of the stability of a Harbour unit that can be a natural boulder or a small sediment, the analysis of the stability against water flow is a question that is located in the domain of sediment stability analysis, sediment transport analysis. It is a very complex problem, because the flow to which these boulders are exposed is turbulent flow. And the flow has behaviors that are random, dominated by randomness, because waves, we know that are typically random processes, which are described by using random models, stochastic models, and also turbulence is described with the theory of probability, by using theory of random processes. Theory of random processes means also that it can have some physical basis, but it's largely based on experimentation. So the theory is verified against experimentation. As I said, the theory may have some physical basis. Still, there is a very significant random component, which means that we have to check model validity and we have to use stochastic models. We have to check model validity with experiments, and randomness means using stochastic models or empirical relationships. Indeed, sediment transport is dealt with in engineering with empirical relationship. What does it mean? Relationship means that we have some measurements that are made in the lab or in the field, in nature, and we find an empirical relationship, analytical relationship, providing a good interpretation of these measurements. And this is the kind of approach that we follow. By the way, I made the same premise when I introduced Harbour engineering. I said, look, in many cases, we will make use of empirical equations, empirical solutions, for the very reason that we have to deal with random processes. And the same thing here. Now, what is then the main problem? The main problem is that I have a segment. So let's suppose that the segment lies over an horizontal plane. Okay? It's not the case for drawings because we know that the segment is not. But let's start with a very simple representation. An horizontal plane where we have a stone. Now I assume a unique shape, but the shape is arbitrary. A stone lying under there, lying depicted here. This is stone lying. The stone is not lying in any way to the bottom, it's free to move. Of course, if it is a spiral shape, it's easier to move. The other hand, we can also move a stone with a cubic shape. And the stone is exposed to a water flow, given water velocity. So this is flow. And the question is, does it move or not? What is the driving force? The driving force or destabilizing force is given by the water flow. The water flow originates, as we know, a forcing over the border of the stone, a forcing that is proportional to the square velocity as we remember. So it means that the increasing velocity has a quadratically increasing force. And then there is a stabilizing force. What is a stabilizing force? It's the self-weight. Self-weight means W means that I have a horizontal component here, which I can call self-implying WH, which is equal to a friction coefficient times W. And of course, the friction coefficient depends on the shape of the needle and also the nature of the bottom and the nature of the needle, the material, also. And this is our problem. And we are using forces in our stabilizing force. And the stabilizing force, the question is it stable or not? In sediment transport, again, we are not much concerned with it. We just assume, we just take note that if it is unstable, sediment transport is continued. If it is stable, we will sediment transport. For the case of the nominals, it's unstable, so of course, the ground can be relieved by the waves. And in the case of the nominals, the flow is influenced by waves, and there is a wave up on the side, and a wave running on the ground side. And in case we refer to a drawing, the side of the drawing is sloped, which means that stability has to take into account not horizontal, but this slope. The slope that can vary between 30 degrees and 5 degrees. Now, this basic problem with horizontal vector has been studied several times, starting from the beginning of 1900, about 100 years ago. Has been studied a lot because at that time, with the growth, the increase of the need of understanding vector fields, why? Because they started with the balance. Most everywhere in Western Europe. They started at the end of 1800, and in some of the cases we did but let's say that it was the last revolution that motivated the need for energy and the need for regulating the Europe. So they started at the end of 1800 with dance, and then at the beginning of 1900, a lot of transport activity. People needed to really understand how cellular transport originated in the volumes of the transport. The second task was filling the reservoirs, which are reservoirs. And also the extract of the development from the first group started to be concerned about the evolution needs. And in several countries, people were started taking care of it. In terms of the seas, the beaches, this application started later, after the Second World War, the concept tourism and the concept of international trade policy. And therefore, it came a bit later. But as I said, about 100 years ago, there were several experiments done to try to understand what is the limit of stability. And this limit of stability is also called the state of incipient motion, which means that it starts to move. And a lot of lab experiments were made. And notably, scientists involved a lot of measurements sheets proposed in 1936 a fine analysis of the equilibrium. Equilibrium, and incipient motion of a train exposed to through a river bed. Ships work on river bed. Actually, he worked in the lab, so he worked through this. But the situation that we want to talk about is precisely the equilibrium to stabilizing and stabilizing forces. When the problem came, stability over unrealistic backwaters and grounds, people prefer to work with more empirical formula. And the formula that they is usually applied for solving the problem in the context of backwaters and the noise is the ratio. And I think you already know it, because usually Professor Alpini teaches it. And I will also remind you of the absolute formula. The absolute formula is purely empirical. So, for the sake of teaching and gaining better understanding of the process, I think it is more useful to refer to the work of shapes, because the sheets start with the stability analysis. What sheets did was a series of laboratory experiments. Then he found he wanted to find a physical explanation of the results. And this is really the way to follow a very scientific strategy. In engineering, people usually prefer to jump straight to the facts. But in science, usually people want to find also an explanation between the theory. This allows us to better understand. And for this reason, we prefer to focus on the sheets and codes, which, by the way, is also used in post engineering. So what we have to do is refer to the stability of this border, and the stability is dictated by, let's suppose, to call the force of flow FW. Okay. So the stability is dictated by a relationship FW is equal to lowercase f W is W, capital W is set okay. This is what sheets wanted to start. This is equilibrium, which means incipient motion, the condition of incipient motion. And of course, here, it's very simple, but we have to plug in the question for destination of FW. So we have to compute this. And an expression for value for friction coefficient. This is fine. It's not very difficult. And we have also to compute the cell weight based on a representative size of the boulder, because of course any boulder has its own self-weight, especially if it's about the boulder, but we can specify a characteristic size, like a diameter, equivalent diameter. Therefore, we also conclude in this expression for W that depends on specific behavior the boulder. And in order to explore this relationship, in order to determine what is the limiting condition for a boulder or even diameter exposed to a wave of given height, it's better if we refer to the situation where the boulder is located over a slope like this. Okay, over a slope with an angle of, if I put I think I indicated in my slides, in my notes, the value there with the. And this is of course a bit more complicated because the self-weight is directed along the vertical direction, the friction stabilizing forces. So the self-weight goes in the vertical direction, but the friction is given by the force, the component of the self-weight that is perpendicular to the slope. So it's not really complicated. And the scheme that we have to follow is here. This is the scheme, okay? So let's try to replicate it here. So that the discussion is a little slower. It's made easier. Then we were talking about what's I think I will have time to make it, okay? This is a very simple schematic representation that refers to an isolated. You know that in practice, the situation is not like that. But let's start with an analysis of the simple case, of the simplest case, and then we will see how to correct the results. Take into account that there are other numbers around everywhere. So I have the angle beta. Side the drawing. It's an angle beta. And let's suppose that we have this cylinder. Let's take it with a square size, okay, and then we will see how to take into account different shapes. And then we have a green forcing. Okay, let's go with F, I think. F, yes. This is the forcing of waves. Of course, during the then we will see the case when there is a down. Of course, the wave goes beyond. Comes back. When it comes back, of course, the velocity, the energy is a bit lower than an atom, but the other end, you see that when it comes back, it's from the point of view of because it pushes down, and pushing down. Also, when it pushes up, the stability is large. And then we have the center weight, which is indicated with W. So there is a weight in blue. Yeah, that's W. Okay. And the component of the center weight. The side of the groin, and this component, okay, let's compute let's start with this. And we can compute it depending on the shear stress which is made by the waves. So there is the shear stress, and then there is the forcing is acting along the surface of the side of the tube against the wave. And it's a surface, the wave is acting against the surface. And so the size of this surface, the area, is proportional to the square of a representative size, which we may indicate with the. In this case, it's the side of the cube, but let's call it just a representative size. And then I have to introduce a shape factor, which I think it is C1 or C2, sorry. C2. What is the shape factor? It is something that relates the square of the representative size, the actual area of the face exposed to the wave. So if it is a perfect cube, then the area is square and the shape factor is 1. But if it is something different from cube, like it is a sphere, then the shape factor has value that is not 1. For a sphere, we know what is a value. The side of this sphere, it would be pi, the square of d. So basically, the shape factor, if I remember, it's not related to pi, it will be pi. But it is fine. In this case, if the cube is 1, if it is whatever shape, we have this shape factor. This is it. And then there is W. Let's suppose that it's immersed into water. There is immersed into water. Why? Because you know, self-weight of a body that is inside the water is lower. If the self-weight of the wood of the material is gas, then immerged in water, you have to subtract the self-weight of water. Therefore, then we have to multiply it by the cube, but this is the value, and another shape factor, C1. Is it correct? It's C1 minus W. Sorry, minus W. And once again, the shape factor depends. It is a cube of perfect cube, again, C1 is 1, otherwise it's different. Okay. But then I have to compute the component that is here that there is more letter, but what I need to compute is the point that is perpendicular to the side of the oil, which is C1 with cube minus lambda of beta. The point that is perpendicular there is obtained by self-weight multiplied by calculating. Of course, if beta is 0, sine is 1, it's self-weight. And if beta is 90 degrees, it's 0, cosine is 0. Okay. So this is the point. And then what is the equilibrium condition? The equilibrium condition is given by how the square equal to the quality of forces C1 the cube gamma s minus gamma cos beta multiplied by the friction factor. I don't remember what is the symbol that I used here. Let's see, probably it's F. Okay, it's no, I used time phi. Phi is the frictional of the material. Okay. Remember always from your background, the friction coefficient is given by the tangent of the friction angle of the material. Good, so I have to start this relationship. And what is my what I want to discover from this relationship? First, let's see what is known. I know the volume size, I know the cube, I know gamma s, as the volume is known, I know gamma, what is known, I know beta, which I know the drawing, I know phi, because I know the friction angle of the materials, so I know what is the friction coefficient to move the drawing. I know everything. I know C1 because I know the shape of the unit. I know C2 because I know the shape of the unit. So now it's I want to estimate the friction, the limited friction of the limited friction means that if I get a higher friction, then the mover is moving. If the friction is lower, the mover is stable. Of course, I put a lot of time to have a safety coefficient, make sure that the movers will be stable. And what determines friction? Weights. So if I know the behavior of weights, I can estimate the velocity of the wave around the wave around. I can estimate the friction of even tiny waves. So I can, the end of the story, estimate is the limiting velocity of the car, the limiting velocity of the car, when I get incident motion, I get the start of the motion. And for now, let me refer to the rundown, okay, and sorry, and then I will see how to adapt the result to study the rundown. Because the rundown is quite easy to estimate depending on the values here. The rundown it's complicated because we are also to estimate the also actually way doing the rundown. And so it's a bit more complicated. So the usual approach is to estimate the equilibrium during the run and then the superficial okay, so I just have to in a way to develop the separation in order to grab T and put down and then she's understood this. So he wanted to check the lab experiment if the tau values are reliable. Keep in mind one thing that you may say, why do I give lab experiment? This is a physical expectation. I do everything and just say, but so you could make an estimate, direct estimate of tau, but unfortunately there are some uncertainty. In the C1, in the C2, there is uncertainty because the representative dynamic. Think about that. How to estimate the representative dynamic of the data, and how to estimate the shape coefficient of that. And then there is the linkage in the theta, which is not yet here, but it is there in practice. So basically, it's the fact that you get the information to see whether this is reliable. So what does it happen if we develop this equation? First of all, we start from this equation that you also see here on the screen. Okay, I'm not sure if I can select it. Let's see. Yes, I can select it. It is more or less the same thing. And here, let me just see. Yeah, okay. The equation actually, it is this one. Okay. And here, it's a little bit different because I express the tangent as sine divided by cosine, so I can in a way group the variables and I get to this relationship here. So basically the critical tau C, is given by the ratio C1 divided by C2, which multiplies gamma S minus gamma D, and because you see that D simplified. So only D remains, just with some manipulation, and cos beta, which multiplies tan phi plus tan beta. So let's suppose that C is equal to C1 divided by C2. So we just indicate with C the ratio of C1 divided by C2, which depends on the shape. For a cube is C equal 1. And then I can write that Tc is equal to C tan phi gamma S minus gamma D, which can be written in this way. Okay, so if I define a dimensionless number, because if you make a dimensional analysis of this ratio on the left-hand side, it's dimensionless. Okay, you will understand why it is convenient to try to study the stability with dimensionless values. Okay, so this number here, tau C divided by gamma S minus gamma D, it's dimensionless. If you account that tau C is tangential forcing, which means a force divided by a surface, and you make a dimensional analysis, and this is self-weight, means forcing divided by the cube of a length. D is a length, this is dimensionless. So this dimensionless number, dimensionless, is equal to C tan phi, which is constant. And this is something that Sheets understood, and he wanted to see if it is true. So keep in mind, first of all, that this dimensionless number is called Sheets parameter, because it was a dimensionless number that was proposed by Sheets. Okay, so is it constant? Is it true? So Sheets wanted to check. Good. Now, let me just check. This is a diagram. It is not very easy to read, okay? And let me see, I want to put this in my notes for two reasons. First, because it's the original diagram by Sheets, so it's interesting. And second, because it also shows other results obtained by other researchers. This is not the second reason. The very second reason why I included it here is that it's open access. But if you go over the web and you search for Sheets diagram, you see some versions that are easier to read. Okay, so you see that indeed under Wikipedia there is the diagram that I used, images. Let me see if there is a nice, a very easy to read one. I think this is probably the one that I prefer. Let me just check. This one, I prefer this. Okay, so here you see dimensionless shear stress is the Sheets number. See that is the same thing. And here on the horizontal axis, there is another dimensionless number, which is called the boundary Reynolds number. It's a dimensionless number that depends on the velocity of the fluid. So Sheets wanted to investigate if for varying flow velocity, the Sheets number was indeed constant. Okay, and I will explain a little bit better later what is this boundary Reynolds number, but just keep into account that here there is this capital U at the numerator that depends on the velocity of the flow. So you see the results. This is the Schiltz curve. It's not constant. The Schiltz number is not constant. But he found that when turbulence is fully developed, it's constant. So when the velocity of the flow is such that the flow originated by waves is fully turbulent, it's constant. Instead, when the flow is not completely turbulent, is laminar, it's not constant. The number, the Schiltz number depends on the velocity of the flow. But when the flow is fully turbulent, it doesn't depend on velocity anymore. So this is what he found. And basically, he concluded, I am interested in turbulent conditions. So that's fine. I mean, my intuition that it was constant, it's okay in turbulent conditions. Okay. And in this diagram, what is above the diagram is instability. What is below the diagram is stability. This means that indeed the equilibrium of the boulder is much more solid in fully laminar flow. So turbulence is an element of instability. Once that you move towards turbulence, you have a decrease of stability, which becomes then constant. However, there is this interesting feature. There is an intermediate situation where the equilibrium is even worse than in full turbulence. So you have laminar situation. The boulder is more stable. Intermediate situation is the situation of less stability. And then full turbulence is constant with a midway stability. But however, we can assume that with waves, there is full turbulence. So we don't have to be concerned about this situation where we are in between laminarity and turbulence. But it is very interesting what he found. So the fact that indeed it is constant, the Schiltz number, which is somewhere, okay, it's not more on the screen, it is constant in the presence of full turbulence. Okay. Let me see if I have other. You see here, in this case, the diagram is more explicit. In showing a constant behavior here of the Schiltz parameter in critical conditions. And let me see. Control. Okay. And also here. Also here, you see that it's indeed constant, and here it depends, the curve depends on several other parameters that we don't consider here, but at the end of the story, it's constant. What is this constant value in full turbulence? Schiltz concluded that it was 4.56. So basically he said, okay, you want to know if your boulder is stable. So compute this Schiltz number, and what is it? Just a second, I think it was here, okay. Compute this Schiltz number, tau c divided by gamma s minus gamma d, and then check whether it's around 0.056, it's critical conditions. If it is above, so we have 0.06, it means unstable. If it is something like 0.03, then it's okay. Even if you go below the minimum, the Schiltz diagram, you are always okay. So this was his conclusion. Clearly, the number that I just gave to you refers to a flat Hilbert bed. So in our case, this number is not to be taken really as an indication, because you see that it depends the number on the fee and, on the friction doesn't really count, but in any case here it depends on this shape factor, and we have also to take into account the inclination, because this is derived, this formula here, under the assumption, I forgot to say it, beta 0. Okay, here it's derived under the assumption beta 0. So actually, there is also the dependence on beta that is to be considered here. Okay, which means that beta is a constant, so it remains a constant. But here, this constant we should say that also depends on beta. Okay, and this dependence is not highlighted here. Okay, very good. So this is the conclusion. And please try to remember how this relationship is derived, because this is a typical question at the exam, like how can you derive the sheets parameter? It's very simple, as you see. You introduce the assumption beta 0, so it's even simpler. Okay. And that's it. And so it is, however, interesting to try to explain how Schiltz made this reasoning, okay? And indeed, he made a more refined analysis of the process through dimensional analysis by means of the Buckingham theorem. No need that you remember it, but I think it is very interesting. It is very interesting to remember the meaning of the Buckingham theorem. Why it is interesting? Because it is the basis also for small scale modeling in the lab. So let's look at the statement of the Buckingham theorem, which says, it is the statement, it is the theorem supporting the dimensionless analysis. If there is a physically meaningful equation involving a number n of physical variables represented by a number of physical dimensions k, what are the physical dimensions? Are the units. So if you have an equation which involves a number of physical variables, look at the units of these variables. There is only length, or there is length and mass. In dynamics, the fundamental units are length, mass, and time. Okay? So how many units should we use among these three to describe these physical variables? Okay, so if there is a physical meaningful equation involving a number n of physical variables represented by k units, then the original equation, let me restart, the original equation can be rewritten in terms of a set of p n minus k dimensionless numbers constructed from the original variables. So this means that if the equation is about 10 physical variables and their units are all of three of them, I can rewrite the physical variables in terms of 10 minus 3, 7 dimensionless numbers, which reduces the complexity of the problem. This is the reason that Schiltz made. So how many physical variables are embedded into this segment stability problem? Okay, the physical variables are tau c, 1, gamma s minus gamma, 2, rho, mass density of seawater, d, diameter, v, velocity of fluid particle. These are the physical variables. This is the most difficult step of dimensionless analysis. Identify how many physical variables are involved in your problem. In our case, it is simple because Schiltz made it for us. So they are 1 tau C, 2 gamma S minus gamma, 3 mass density of seawater, D and V. And they are 3 units. So 5 minus 1, 2, 3, 2-dimensional number. So he understood, he wanted to find 2-dimensional number to describe the problem. And what are these 2-dimensional numbers? One is the shift parameter. And the other one, he found precisely the Reynolds number. And here is the particle Reynolds number, Reynolds star, which is the horizontal axis of this diagram. It's given by the product D times U star, we will see what is U star, divided by μ, where μ is kinematic viscosity of water, and U star is given by this equation here. U star is equal to tau, which depends on wave velocity, divided by rho. Tau is friction. So basically, we can write that tau C divided Schill's number is a function of the Reynolds number. And this is the physical equation describing the process. You understand what is the power of dimensional analysis? When you don't know the physical theory behind the process, you determine the number of physical quantities, the number of units, and then you express the physical quantity in terms of dimensional numbers. So he could find that the nature of the equation, of the true equation, of the theoretically based equation, was of this kind. And then he explored it with the diagram. That's it. And he determined that in turbulence, in free turbulence, the Schill's number is constant. And it is a very powerful way for estimating the stability of block of Harbour units, because you go into the diagram, you stay here on the right, because we can assume turbulence, and you just need to estimate the Schill's number here, tau C divided by gamma S minus gamma times D, and if it is lower than something that you can take like 0.04, that's fine. That's fine. And it is a fully physically based reasoning validated by lab experiments, and the fully physically based reasoning was derived with a dimensional analysis. It's very nice and interesting, an interesting approach to drive the development of an empirical relationship, because this is empirical, it's purely empirical, it's derived in the lab. The value of the constant is derived in the lab. But still, we have the problem of taking into account the fact that the side is sloped, there is an hiding factor. So what are these corrections that we have to make? Okay, because the problem is solved for a flat bed and for a single unit, but then we have to take into account first that we have waves and currents, so we may have the superimposition. This is quite easy. I mean, you don't have to remember this relationship. We can assume that there is a linear superimposition of the friction given by currents and the friction given by waves. And these two frictions are estimated depending on the velocity of waves, this prime, and the velocity of currents, this the opposite, the other way around. The velocity of currents, lowercase u prime, and velocity of waves, uppercase u prime. Okay. Don't need to remember this. Okay. There is a coefficient, and FCU and FW, no need to remember. Okay. And effect of slope. Okay, we may have two slopes. We may have a slope along the side. On the side. But we may have a slope in the longitudinal direction, because the ground is the slope from seaward to landward. Landward to sea, it might be a longitudinal slope. Then there is a lateral slope. Slopes. Therefore, I need to introduce two coefficients for correction. You see that in the left-hand side here, you have a corrected critical tau, which is obtained by multiplying the shields critical tau by two coefficients, k beta and k beta 1. And here you see the way to determine this k beta. Be careful. K beta, they have two values. And here we introduce the analysis of the rundown. The two values of k beta are for run up and run down. So the upper one is run up, the upper one is run down, the lower one is for run up. And k beta 1 is computed in this way, depending on the angle beta 1, okay, which is the slope in the longitudinal direction. No need to remember these formulas, just keep clear in your mind that if you have a slope, possibly two slopes, you have to correct the stability, the critical tau, the shield's critical tau. And then there is hiding. Hiding is the fact that you have more than one boulder, more than one unit. There is no formula here. It is just mentioned here that you have an empirical formula which Sheets himself derived. Okay? No need to remember more than that. And then there is the effect of the Harbour unit shape. What are these shapes? Here there is a link, an interesting Wikipedia page, which gives to you a complete list of the shapes. Let's see if the link is here or just 1 second. Okay. Where is the link? I don't think it is here. Let me just see. Because here is a link to the tetrapod, but and the tetrapod is this size, but I have a link, I'm sure, in my lecture notes to a list. Wait a second. Let me see if it is here. Or let me see. I think it is somewhere here. Just 1 second. Let me see this link. Oh, it's the same. Okay. Quite sure that I have a link to a PDF which gives to you. Let me go, just give me 1 minute. Let me go back to design of drawings. I think maybe here. Not here. Let's see. Don't think it is here. Again, stability. Okay, anyway, I can't find it now, but there are several. So the equation is not what I wanted to click. There are several shapes, and here there is an example of tetrapods, but similar design. Let's see. I think you can refer to this, but this is without. Okay, this is another shape called Acmon. And this is the dolos. This is a picture of the dolos. And the dollars, you see that they have a shape that is in 3 dimensions, like the tetrapod, but it's a different shape. And let's see, here they are. And you see that they are like a double T. It's indeed, and they are quite huge, as you see. And here they are in place. And here it is another one. Okay. And then beside the dolos, there is stabilopod, there is no ink, acropod. Let's see this one, if there is. Okay, this is another shape. You see there are several of them. Okay, so basically I found what I was looking for. And for each of them, there is usually the producer gives to you corrective coefficients for the sheets formula. Okay, that's it. 4 sheets. Here we are. Okay. And for sheets, make an effort to remember how the sheet formula is derived, which is just enough for our purpose. And you don't have to remember empirical relationship, just how it is derived, the sheets formula, which is enough. Now, I mentioned also the Hudson formula. I think you know it already. Here there is no physical basis. It's just a formula that finds a limiting value for the weight capital W of each armor unit. So on the left-hand side, what you see here is the weight of each armor unit, which should be larger than a ratio which has at the numerator reference value for wave height, which is about 1.27, the significant wave height at the top of the structure. Significant wave height means that you get, as you may remember, you get a series of observations of wave height, and you get the upper third, and the lower limit of the upper third is the significant wave height. Okay? And you take the cube here at the numerator, and gamma R is the specific weight of the Harbour material. So basically here you have something related to the weight of the Harbour material, of the armor material. And at the denominator there is KD, an empirical stability coefficient, and then you have gamma R, again, weight, specific weight of the Harbour material, minus gamma specific weight of water, and B is the side slope. KD has to be estimated. Several approaches has been proposed. Usually the producer of the armor units give you an estimate of KD. So this formula is much simpler. I mean, it's just something that you have to take for granted. You have to plug in the characteristic values for the given armor unit, and then you get an evaluation. And here you see the expression of a critical number that is defined in order to estimate the value of KD, but let's assume just that KD is derived, is given by the producer. You don't have to remember as far as I am concerned the Hudson formula. I don't know if Professor Archetti wants that you remember it. I don't ask anything related to the Hudson formula. It's just enough for me that you know that it is an alternative to shields, it exists, and it's purely empirical. Okay. I think that's it for the stability of armor units. Do you have any question related to this? Okay, no questions. So We still have some 10 minutes to go. Let me mention to you, given that we have a last one lecture, what is my plan for the next time in order to also for you to make a plan. Next time, I want to make an exercise, assessment of stability of armor units, and here it is. So it refers to a groin with a slope of 30 degrees, is exposed to 30 degrees is more or less 1/2, is exposed to a significant wave height of 2 meters at its tall. The wave forcing originates a top wave run-up velocity of 4 meters per second and a top wave run-down velocity of 1.5 meters per second. Is much lower, of course. The value of the wave-related friction factor FW is 0.1, plausible value for large stones, while the density of seawater is 1,000 plus 24 kilograms per cubic meter. And let's forget about forcing by currents. So the groin is protected with boulder with the characteristic size of 1 meter and the specific mass of 2,500 kilograms per cubic meter and friction angle of 40 degrees. So verify the stability of the armor units with respect to the run-up and run-down by using the Sheets criteria. And we have formulas for computing the friction depending on the water velocity, by assuming that hiding effects and effects of armor shape are negligible, and verify the stability of the armor unit with the Hudson formula by assuming NCR equal to. So I want to make this, and next week, I think we will have time for last lecture to discuss about the nice topic of climate change, which is not related, not directly related to the exam, but it is very much relevant for any design operation that is related to sea conditions, because you know that we are expecting a sea level rise in the future, which is associated, which will be, it is considered to be associated to an increase in extreme wave height. And therefore, there is a relevant question in general, how to make engineering design of environmental structures and infrastructures in the presence of climate change. What kind of correction we have to make to our, or what kind of update we have to make to our proceedings for engineering design. And the topic is so relevant that next year, as you may know, we will substitute the course Harbour engineering with a course on climate change adaptation, which is dedicated again to Harbour engineering, but with a larger focus on climate change adaptation. And so I want to discuss this issue with you, and I think that the exercise and the discussion of climate change will close our course, our part. So it means that you don't have to refer to the two links, the last two links, dredging in Harbour basins and design of breakwaters. Design of breakwaters is usually carried out by Professor Archetti, but we agreed that I would provide an additional information on it, additional details, but we don't have time to do that. And so the last two links, you have to forget them. I leave the link there for your information. I'm not removing the links, but just be advised, as I said at the beginning, that our exam, my exam in particular, is based on the links on the lecture notes that I discussed during the class. There is nothing related to something that I didn't discuss here. Of course, if you have any question, even later on, you can contact me. And if you want individual explanations, we can also set up a virtual meeting, no problem at all. I am fully available. The exam, it's an oral examination. Usually we don't ask students to make calculations. Maybe very simple ones, but very simple, something that you can do with a pocket calculator. You don't need, we never ask to do anything on the PC. So the exercises that we have made, these are, and I explained it at the beginning, these are not a subject of the exam. So I strongly advise you to also to improve your coding skills, but nothing related to the exercises can be asked to the exam. And we usually make the exam together, which means that we sit down together and I make the exam first, vice versa, and then the other professor follows. And usually we, yeah, we try to do it the same day. And but on the other hand, we are very flexible because we are first students only. So if you ask to make the exam with me 1 week later, usually I say yes. The only thing where we cannot be flexible is your physical attendance, unless you are an Erasmus student that already left. We are only allowed to make online examinations for Erasmus students who already physically left. Otherwise, we need to see students face to face in order to make the exam. This is an explicit requirement by the rules. Any other questions? Okay, I think we can stop here for today and see you next Wednesday. Yes, yes, we need to wait the end of the lectures. So I'm not sure when she ends. So I defer to her. The name is available. So the first day after closure, we can make the exam. Okay. So I'm not sure when she wants to conclude because you know that she had also common problems this year. So I'm not clear on the calendar. Usually she used to close everything by the mid of May. And last year we made the first exam in May 20, something like that. I think that also this year we will have a similar thing. But please refer to email. You can also write an email if you're interested. And usually I'm about it. And you can tell her that whatever she decides is fine to me, but I will tell you. Okay? Good. Thank you very much.